All right, in section 2.2, we're going to continue with graphing, and we're going to look at some more concepts like maximums and minimums and increasing and decreasing and things like that. So let's take a look here in section 2.2. First thing I'm going to do, however, is zoom in a bit so we can get the picture blown up. Okay, that should work. And what this problem is going to ask is it's going to ask for relative maxima and maximum and relative minimum. Let's start with relative maximum. I'm going to draw these shapes and I'm hoping it's pretty simple to see what we mean. So a relative maximum is when the graph changes from increasing to decreasing and it creates a hump or a mountain. So the peak of that mountain will be the maximum. It will also study something called a relative minimum. It's the same idea. It's when the graph changes from decreasing to increasing and it creates a valley. And the bottom of that valley would be the minimum. So this question is just going to ask two things. It's going to ask where does the maximum or minimum occur, and then what is it? So it's going to ask two things. It's going to say where is the max? When it says where is the max, that's going to be an x value. So first off, we can hopefully easily see that the maximum is right there. So there's a max. And then the where is, what x value does it have? So we go straight down to the x-axis and we record that x is 3. Then the second question it's going to ask is what is the max? And when it asks that, it's asking for a y value. So we want to record the y value of this max. To do that, you go straight left till you get the y-axis and record the number. And it just so happens to be another 3. Just a coincidence. Okay, so that would be the values for the maximum. Now the next part's going to ask for the minimum. Now in this case, there's two of them. So we have one right here. And we have one right here. And that's okay. It's possible to have more than one. It's any point where we get this dip, this valley in the curve. So it's going to say, where are these minimums? Which are the x values. And we had two of them here. So you can kind of see the dots kind of outlining right there. We had 2 and 4. And that's going to say, what are the minimums that you're looking at y values. So we go straight to the left. They happen to be lined up perfectly. So we go straight left and record the y value of -1. And we have to record it twice because there's two of them. Okay, so that would be relative maximums and relative minimums for the first problem. For problem 2, and I've zoomed in quite a bit here, it's also asking for max and mins, but we're given a graphing calculator output of the actual function. So our function is up here on the top. It's 2x cubed plus 3x squared minus 36x plus 9. And if I graph that in the graphing calculator, we get that. And so we can quickly identify the maxes right here. And if we do this correctly, we go straight down to find where is it. Now this tells us that the left part of this graph is at -5. The rightmost point of this graph is 5. And they go by ones. So this is -4, -3, -2, -1, 0, 2, 3, and 4. Okay, so that's the x scaling shown on the bottom of this graph. And we can see that the maximum, the where of it, is x equal -3. On your homework, you just have to type in -3. You don't have to type the x equal. And then the what of it is going to be y equal to what? Well, in this one, we can go over, and the problem is it's in between those tick marks, so it's going to be harder to figure out what it is. In fact, this one's interesting because the scaling, it starts at -120, it stops at +120, and it increments by 20. So this is like -100, minus 80, minus 60, minus 40, minus 20, and 0. And this is 20, 40, 60, 80, 100. So we're in between 100 and 80, but we're not sure exactly where it is. So to solve this, we have to take this minus 3 and plug it into each of these x's for the function. Because remember, this function is really the y value of the curve at any given point. So we're going to plug in negative 3 and get 2 times minus 3 to the third plus 3 times minus 3 squared minus 36 times minus 3 plus 9. And from last class, we had learned that negative numbers to odd powers, the minus sign will stick around, so this is going to be minus 27. We also learned that minus numbers to even powers, the minus will go away. So this will just be 3 squared, which is 9. These two minuses will cancel, so you get plus 108, plus 9. And you can double negative 27 and add it to positive 27. And if you do all this, you will get the y value when x is 3 of the function is exactly 90. So my drawing 90 would be about right there. So my drawing, I was a little bit above that, so I might have guessed it right, but to get the exact answer, just plug your x value into the function. Okay, now for the minimum, we can all see that it's here. And we can identify the x value as 2. So the where of it would be x equal to 2. The what of it, which is the y value, what is it, we have to do the same thing. So I can estimate it. I can pull this over. Looks like it's close to minus 40, maybe negative 38 or so. Well, let's just plug it in and figure it out. So we'll plug in 2 whenever we see an x. A little bit easier. I don't have to worry about minus signs here. 2 to the third plus 3, 2 squared, minus 36 times 2 plus 9. This would be 2 times 8 plus 3 times 4 minus 72 plus 9. And if you 16 and 12, add those up, subtract 72, do all that arithmetic, you should get that this would be equal to minus 35. So the y value there is minus 35, which you can see pretty close to what I've drawn there, in between, closer to 40 than 20, past the halfway point. Okay, so that's one where we can easily see the x values of the min and max, and then we have to plug them into the function to get the y values. Okay, for problem 3, we're going to have to learn 3 types of symmetries. So you can have graphs that are symmetries or kind of mirror images of themselves in 3 different ways. Is when, actually let me put the axes in here, so this is x and y, x and y, x and y. Okay. One is when you have a symmetry about the y-axis. So this is called y-axis symmetry. Now we had seen that this was the parent function for any x raised to an even power. So these are also called even functions. And what we get is, what happens is you have positive, if you have positive x, let's say we have 3, let's say this is x squared, the easiest of the even functions. So if this is x squared, 3 squared would be 9. So this point here would line up with 9. What's interesting about this is also minus 3 would also line up with 9, because minus 3 squared would also give you positive 9. So the way we would write it is, when you plug in a negative x value into the function, you get the same y value, which we call f of x. Okay, the other one, most common, is called origin symmetry, because if you flip this thing across the origin, you'll get, so imagine we put a mirror at an angle across the origin, it would reflect the bottom, the third quadrant into the first, and it would look the same. So this is called origin symmetry. And we also noticed that this was the parent function for when x is raised to an odd power. So this is also called an odd function. Now what's interesting about this one is, let's say I have x to the third, and I pick 2. 2 to the third is 8. So we get 8. Minus 2 to the third, the minus is going to stick around, and we're going to get minus 8. So in this one, if we plug in a negative x value, we also get a negative y value. Okay, those are the two most common. Now there is one more possibility, and that is if we have x-axis symmetry. So if you were to put a mirror on the x-axis, it would reflect the top part and it would look just like the bottom part. This is x-axis symmetry. And we don't call it even or odd because technically this is not a function because it does not pass the vertical line test. So if we learned this class or two ago, if we pass a vertical line, it hits more than one point. So this is going to fail the vertical line test. Therefore, it's not a function. But we might still see these graphs. They're not functions anymore. They're still graphs, though. And what you end up getting is you solve for y. You solve for y, and you get some plus or minus some function of x. So you isolate y, and if you end up having to perform your arithmetic and you have a plus or minus and then some stuff, that's going to give you a portion of the graph above and a portion of the graph below, and it could just so happen that it has x-axis symmetry. So these are all the things you have to check what you would get. So we're not going to use numbers here. We're going to actually plug in minus x into the original function. So here's the two possibilities, the most common. We plug in minus x into here. If we get the exact same function out, then it has y-axis symmetry. So if we plug in minus x and we get the result to look like this, x squared minus y cubed equals 9, then you have y-axis symmetry. If, on the other hand, we put in negative x and we get negative x squared plus y cubed equals 9, actually equals minus 9. So we have the exact opposite. Everything has been flipped. So positive x squared becomes minus x squared. Minus y cubed becomes plus y cubed. 9 becomes minus 9. If we get that, then it has origin symmetry. So in all these problems, what you have to do is plug in negative x. So instead of x squared, we're going to plug in negative x. And we're going to see that when I square this minus, it's going to go away. So I have a negative number raised to an even power. The minus will drop, and you have x squared minus y cubed equals 9. And now I just compare this to these two. Does it match either of these two? Well, the blue one, if you look, you have x squared, minus y cubed equals 9, 9. Everything matches, so it does have y-axis symmetry. And for the most part, if you have a function, you're not going to be able to select more than one of these. It's only going to be one or the other. Now let's see how you would check for x-axis symmetry, even though I've already picked an answer. We would have to isolate y. So we would say minus y cubed equals 9 minus x squared. To get rid of this minus, I can flip everything and call it positive x squared minus 9. To get rid of that 3, we would take a third root of y cubed, which would mean we would take a third root of x squared minus 9. Now, if you have y to the p, some power, equals some x, then y equals the pth root of x. And if p is even, you add a plus or minus. So we're used to taking just a regular square root. Well, the regular square root is power 2, so we add a plus or minus. But if p is odd, if the power is odd, like in this case to the third power, you do not add plus or minus. Do not add plus or minus. So this answer over here is just y is equal to the third root of x squared minus 9. So it's only going to be the top portion of this graph. It's not going to have this bottom portion. So it will not have this x-axis symmetry. Okay, for 4, it's very similar. So we want to check the different symmetries. So let's check x-axis first. For x-axis, you have to isolate y and see if you get some plus or minus stuff. So let's isolate it. We have y squared equals 18 minus x squared. To get rid of that squared, we take a square root. Now, because that is a 2, an even power, I do have to add plus or minus. So it would be plus or minus the square root of 18 minus x squared. And because we have this plus or minus, we're going to say, yes, it should have x-axis symmetry. Let's check for y-axis. For the y-axis symmetry, you plug in, you replace x with minus x, and you see if you get the exact same function out. So we replace that x with minus x, and we see this is going to be x squared, and we have plus y squared equals 18. This is the exact same as what we started, so it does have y-axis symmetry. For origin symmetry, you substitute in negative x, and you see if you get negative f of x, which is another way of saying if we replace x with negative x, we can replace y with negative y, since f of x is y. So we're going to replace both negative x and y with negative y, and we're going to see if we get the same equation out. So we would get negative x squared, which is x squared, negative y squared, which is still positive y squared, equals 18. That's the same as what we started, so it should have origin symmetry. Okay, so we have all three, and I had said, well, with a function, you should only have one of these three. But let's see what's going on here. There's something a little interesting going on here. So this is of the form x squared plus y squared equals a number squared, which we called a radius. This is the equation of a circle centered at the origin. You saw this last class. So I can rewrite this as x squared plus y squared equals about 4.2. It's a few more decimals than that, but that's fine. 4.2 squared. So this is just a circle at the origin with a radius of 4.2, which we can quickly graph. So there's going to be a dot just past 4 on each of these lines. 4.2. And if we connect that smoothly, and being able to visualize this is going to be highly dependent on my drawing skills. But what we can see is that, yes, this circle does have x-axis and y. So if I folded the bottom onto the top, it's going to fit. If I fold the left side onto the right side, it's going to fit. If I fold the lower diagonal onto the upper diagonal, it's going to fit. Everything's going to match. So it has all these different symmetries. But and keep in mind, it's going to fail the vertical line test. So this is not a function. So yes, it has all these symmetries, but it's not a function. And we're going to mostly want to deal with functions. So you won't see this too often. In most of our cases, we're going to only pick one of those three, or possibly none. Okay, so number 5, we're going to do the same thing. We're going to check for even. For an even function, I should get the same thing out. So I plug in negative x, I should get minus 5x. X cubed minus 5. If we plug in negative x for an odd function, I should get the exact opposite, minus x cubed plus 5x. So we just have to plug it in and see which one it is. Does it match completely? Is it the complete opposite? Or neither would be some mismatch. So maybe half of it matches, half of it doesn't. So notice that this is completely opposite, all opposite. This one is all match. And then this one would be a part match. So it might be x cubed plus 5x. So the first two match, but the second two don't. Or maybe it's minus x cubed. And then we have minus 5x. So in these cases, you get a part match, but not a full match. So that would be the case for neither. So we just have to plug in negative x and see which case we get. Plug in negative x, and we get negative x to the third minus 5 times negative x. A negative number to an odd power, the negative is going to stick around, so we have negative x to the third. These two negatives, however, will double negative cancel, so we get plus 5x. And so notice that this one matches this. So they're exact opposites. So each one is an opposite of the original one. So it's an odd function. Now the nice thing about this is odd will match up with origin symmetry always. And if you had recorded that it was an even function, that lines up with y-axis. And then neither will always match up with neither. So you kind of have less thinking to do there. If you get the first part right, then these things match up like this. We picked odd, or we didn't pick it, we solved it to be odd, so it has origin symmetry. Okay, in 6, we're going to do the same thing. So we're going to replace x with negative x, and we're going to get negative x squared minus 3 times negative x. And it's going to be, because it's an even power, the minus sign will go away, so you're just left with x squared. But these will double negative cancel, so you get plus 3x. And we see that we have a match here, but we have a mismatch here. So the minus and the plus do not match, but the first two match, so this is a partial match. And if you get a partial match, that's going to be neither. So it doesn't have symmetry on either of these things. So it's not even or odd function, and it will be no symmetry about any axis. Okay, in 7, there are going to be a bunch of questions, and I'm not, like, if you scroll below the picture, you'll get a bunch of these blanks that you can fill in. That's mostly the way the homework is laid out. But I just want to have the picture zoomed in on, and then our questions right next to it, so we can just fill these in next to these questions. So the first thing it asks for is a domain. Now the domain is always x values, and you're always considering this left to right. So you're saying, okay, this graph with this arrow means it goes off to minus infinity. And then it has this slanted upwards arrow, which means two things. It's going to keep going to the right, but it's also going to keep going up. So there's two infinities there, an infinity going up and an infinity going to the right. Now for the domain, I only care about the blue. So in this one, I start off at negative infinity, and I'm on this flat curve, and then I go down, and then I go up, and then I'm going to keep going up and to the right. So the domain on this one is minus infinity to infinity. It's going to be everything. Okay, the range is a little trickier. The range is only the y values. And I'm always going bottom to top. So what's the bottommost point of the graph? What's the topmost point of the graph? So the bottommost point of this graph is this minimum point right here. It's the bottom of a valley. And for range, I care about the y value for that point. So it's at negative 4. So the graph starts at negative 4. And then it's going to go up and up and up and up to the red infinity up there. So it's also going to go to infinity. Now infinities always get parentheses, but we have to think about this 4. If the graph touches the line that has 4, then it's going to be included. And if you look closely, it does. So this is going to get a bracket. So domain and range, you do have to consider brackets and parentheses. If it's touching or not, or if it's an open hole or a filled-in dot, you would have to consider that. Okay, so that's domain and range. The next thing it asks for is x-intercepts. X-intercepts is where it touches the x-axis. And there's 2 spots right here and right here. And we just have to record the x values for those dots. So 1, 2, 3, 4, 5, 6, and 7. So 3 and 7 are where the graph touches the x-axis. For the y-intercept, that's where it touches the y-axis. And so it's right here at this corner, and that has a y value of 21 if you count. Okay, for the next part, this is new. So all this we've seen before until this point. So we're looking at intervals for increasing and decreasing, or constant. So to do these, I always go left to right. Left to right, and I'm only going to use parentheses. So unlike domain and range where I have to consider brackets and things like that, these intervals will only use parentheses because you're going to see that some of the numbers are shared. So some of these numbers, things change from increasing and decreasing, and they're going to show up in both intervals. So for a function to be increasing, as I move left to right, it's going to look like this. It's going to go up and to the right. For a function to be decreasing, as I go left to right, it's going to be going down and to the right. For a function to be constant, as I move left to right, it's a flat line. So let's not do these in order. Let's do these in order of left to right for the graph. So as I start at the leftmost point of the graph, it is flat. And it's flat until this point right here. So this starts at minus infinity. So technically, I had to go out to negative infinity, and then it's flat that whole time. Now this is where most students make mistakes. They want to write down the y value of this at 21. We do not care at all about y values here. What we're trying to identify is what are the y value doing? Is it changing? Is it getting smaller or bigger? So I'm only interested in the x values at which these y values are changing. So from negative infinity until x is 0, this line, it is constant. So from minus infinity till x is 0, this thing is constant. Now one nice thing about these is you'll always pick up where you left off. So the next thing it does, from this point, my y values start to get smaller. So they're getting smaller till this point here. Because they go from 21 to 18 to 12 to 6, etc. And so it starts decreasing from 0 to this x value, which is, let's see here, 1, 2, 3, 5. So again, I only care about the x value here. So it's going to go decreasing from 0 to 5. And then we're going to pick up where we left off for the last segment. From 5 until infinity, because it's going to keep going to the right, it will be increasing. It's going up. And one thing about this is you should start where the domain starts, and you should end where the domain ends. And this point here, where it switches, should be a max or a min. Okay, this one was kind of unique. The 0 that was in both, where it switched, is technically not a max or min because it's a corner. Okay, so that's kind of a tricky part, but just go left to right. Make sure you start at where your domain starts and you end where your domain ends, and then these numbers in between should match. So 0 matches 0, 5 matches 5. That's where you left off, and just try to figure out if you're going up or down. Okay, the next one asks us if it has a relative number which f has a relative minimum. So we just saw that point. The relative minimum was right here. It occurred when x was 5, and I think it's going to ask us for its value. Its value is -4. So you would say the x value for the minimum is 5, and the y value for the minimum is -4. Oh, actually, that's the answer here. So the relative minimum of f is -4. Okay, this one's going to ask, when x equals -1, what is y? So one of my students in my face-to-face class asked, what's f? And I said, well, f is just another name for y. We use f because it's a function, and we've talked about how, what functions are. So we use function of numbers, in this case, x numbers. So this is when x is -1, what is y? So you have to go to -1 in the x, which is right here, and you have to go to the curve. So to get to the curve, I have to go straight up, and then you record what is the y value at that point. The y value at that point is 21. This one asks kind of a similar question, but in a different way. It says, let y equal -3, and what does x equal? So let y equal -3, what does x equal? So in this case, you go to -3 in y, 1, 2, 3, right here, and then you go and see what your x is. Now notice there's actually 2 of them. So you hit the graph twice, one at 3 and one at, actually I think that's 4. One at 4 and one at 6. So you actually have 2 answers to this, 4 and 6. Okay, the last one is f even, odd, or neither. So for it to be even, the graph would have to be symmetric about the y-axis. Now if you look at this one, it kind of has that hump feature, but that would be symmetric not of the y-axis, it would be symmetric of this line, x equal 5. But it still wouldn't be symmetric because you'd have to have a line going like this to match this one over here. So it is not y-axis symmetric. Odd, it would have to look like this. It would be mirrored about the origin. So for that to be true with this drawing, not only would we have to flip it up and down, we'd have to flip it left and right, so it would have some portion like this, down here in the third quadrant. And it actually would go up like this too. But we don't see that, so that one's out too. So the answer here is neither. It doesn't have any of those symmetries. Well, there's a lot there. We'll do a couple more to get practice and practice on your homework, and let me know if you struggle here. I see students struggle a lot with these because you confuse your x's and y's, and am I recording x's, am I recording y's, am I looking for x's? So we'll practice here. Okay, so 8 is really similar. We're going to go in here and say the domain is the x values. Now we're going to notice that this thing, it's kind of missing an arrow here. Usually they put little arrows to indicate that it keeps going. So if it does, then that means it's going to keep going left for -infinity, and it's also going to keep going down for -infinity in the y. And so what we get is for the domain, it starts at -infinity in the x. So again, we're only looking left to right for domain. And I'm down, and I'm coming up, and then it goes up here, but then it stops, and it stops right here at x equal to 5. And it does touch x equal to 5, so we use a bracket. So be careful here. I have students that want to say it goes on to infinity, but it doesn't. This stops at x equal to 5. There's no line drawn for 6, 7, 8, or anything else. Now the range, it starts at -infinity also. And this is where I also see students make errors. What's the top of this graph? So range, you go bottom to top. The top of this graph is this maximum right here, and that occurs at y equal 3. So you're going to say 3, and it also touches the line of y equal 3, so it's going to be a bracket. Okay, the zeros of f, the zeros are the same as x-intercepts, where it touches the x-axis. Well, it touches the x-axis right here at -1, and it touches at 5. So we have two spots, -1 and 5. This one says, when x equals 4.5, what does y equal? Okay, this one's a little harder to see. It's because this is a pretty small graph, even when I zoom in. 4.5 is right here, just to the left of this big dot. And if I go up, it hits right there. So from 4.5, you go up until you hit the graph, which is right there. And then you go straight left to read the y value. And the y value is +1. So we have a +1 for that answer. Okay, the intervals of increasing or decreasing. So again, I'm going to go left to right here. So we have to do this left to right. And increasing looks like this, decreasing looks like that. So notice, as I'm moving left to right, I'm going up. So I'm going up, 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 and then right there I flatten out. So the x value for that spot is 2. So it's increasing from -infinity to 2. And then it's going to decrease from 2 until decrease, decrease, decrease until this spot right here, which is 5. So it's only going to decrease from 2 to 5. And for these, you always use parentheses, no brackets. So it would look like that. And notice again, that point, that x equal 2 was the maximum. So that maximum is where we switched from increasing to decreasing. So this point right here, the point where we switched was the max. Okay, let's take a look at the next one. It says, what are the values for which f of x is less than or equal to 0? That's another way of saying when is y below the x-axis or touching it. So let me write this in words. This is saying when is y below or touching the x-axis. And we do need interval notation here. So notice it's below the x-axis from -infinity in the x all the way up until this point. In fact, it's also touching the x-axis at that point. That point is -1. So we're going to have, this is -infinity to -1, but it's touching -1, so we use a bracket. Here's the tricky part, and here's where most students will miss this. It also touches the x-axis right here when x was 5. It's not below there, but it's touching there. So we have to union that with just 1 point, x equals 5. Tricky. All right, the next part says, what about a relative max or min? Well, we already found that max, everything to the max. It was located at x equals 2, so this max. So this is h. Let me answer it over here. The x value for the max was at 2, and the y value for the max was at 3. Okay. The values of x for which f of x equals 3. The values of x, well actually I shouldn't erase that because it turns out to be the same answer. So this says y equals 3. What does x equal? So we go to y equals 3 line, which is right here, and we go until we hit the graph, which is right there, and then we go straight down and collect the x answer, and x was 2. So that's just another way. They just asked us to find the maximum again. Last question. Is f of 3 positive or negative? So this says x equals 3. Is y positive, which means it's above the x-axis, or is it negative, which means it's below the x-axis? So we go to x is 3, and we go up, and since I went up right away means that that's a positive number. So we would pick positive for this. If I had gone down to get to the graph, it would have been negative. Okay, so that's 8. Okay, so 9 is what we call a piecewise function. We have seen these before, but we're going to do, I'll show you a little more detail on this since we haven't, before we just plug numbers in and got numbers out, but I want to show you just a little bit more. So first off, notice that this function h, notice that if you plug 2 in here, let's say we plug 2 into this, you would get 2 squared minus 4 over 2 minus 2. 2 squared is 4. 2 minus 2 is 0. You get 0 over 0. Now, we made this argument earlier. You cannot divide by 0, so you get undefined. So to get around that, they say, well, okay, when x is 2, let's change the value of the function to the number 8. So that can kind of get around this in that I would have a problem at x equal 2 in this one, but not in the bottom one. Okay, but there's also something we can do with this top function. So I think we had seen this, maybe, maybe not. If you have two perfect squares, x squared minus b squared, you can factor that into a minus b, a plus b. So this x squared minus 4 is going to factor into x minus 2, x plus 2. But we have an x minus 2 on the bottom. And so those can cancel. But before you cancel them, you have to say, wait a second, there's going to be a hole at x equal to 2, because that 2 still would have caused a problem in the original problem. It would have caused a divide by 0 error. What's interesting is, once I cancel those two, my function is just x plus 2, is just that numerator portion. X plus 2 is a super easy thing to graph. It's a straight line that starts at 2, okay, so this graph is going to start at x plus 2, would start at 2 in the numerator, and it has a slope of 1. So I go up 1 to the right 1, up 1 to the right 1. So let's pick a number here and just calculate. Let's say I have x is 4, then 4 plus 6, it's going to be at 1, 2, 3, 4, 5, 6. Here's 6. So I have another dot right here. Let's try 2, because 2 is the problem child. At 2, this function should have given me 4. 2, 3, 4. But instead of a filled-in dot, I get a hole. So this is really a red line. Should have been red here. This is really just a line that goes through these points. In fact, it will hit at minus 2 down here, so it's also going to go through here like that. And it's going to go off to infinity and left and right. But that 2 would create a hole there. So I should have gotten 4, because 2 plus 2 is 4, but 2 in the original problem caused a divide by 0. So instead, we're going to put a dot at 8. So we have a filled-in dot at, let me do it green here. So this one says put a dot at 8. So that's our function, this combination of red line and then green hole and green dot. Okay, but you don't need actually any of that. In this problem, all you have to do is, I just show it to you to kind of see what it would look like. All you have to do is plug in these x values. So this says x is 3. So first you have to decide which function do I plug it into. Do I plug it into the top one or the bottom one? Well, the bottom one we only use if x is 2. This not equal sign means you use for any value but 2. Use for all values but 2. So x is not 2, or excuse me, x equal 3 is not 2, so we're going to use this 3 into the top equation. So we would do h of 3 is going to equal 3 squared minus 4 over 3 minus 2. Just replace those x's with 3's. This is 9 minus 4 over 1. This is 5 over 1, which is 5. So we get 5. You can probably see it on the graph. When x is 3, we have a y value of approximately 5. If I drew it to scale. Okay, let's try h of 0. X is 0. So that's also not 2, so we're going to use the same function. 0 squared minus 4 over 0 minus 2. This would be minus 4 over minus 2. This is double negative cancellation, positive 2. In fact, that's where we started the graph. So 2. Now, h of 2. This is x equal 2. So if x equals 2, I use this one, and I just record the answer is 8. Now, sometimes it is a different equation, so you would have to crunch it out. But in this one, they just give us a number. So when x is 2, your y value is 8, and that's that green dot right there. Okay, for 10, we are given two piecewise functions. So it says when x is smaller than 0, use negative 3x, and when x is bigger than 0, use positive 3x. So to solve these, first I need a picture. Once I have the picture, the rest is pretty simple. We're going to pick x values and solve for f of x values. And I like to use, let's use a couple negative, minus 3, minus 2, minus 1. Always use 0, use 1, 2, and 3. So for all of the, let me see if color can help us here. For all of these, excluding 0, we're using this one, the minus 3x, because this says when x is less than 0. Notice it says not including 0. So not including 0. We use the top one. So this would be minus, plug in these x's, minus 3 is out front times minus 3 from the x would be positive 9. Minus 3 is out front with the minus 2 from the x value is positive 6. Minus 3 is out front, and then the x is minus 1, positive 3 because of double negative cancellation. Okay, then it says 0 or bigger, use this one. So 0 or bigger, use positive 3x for your function. So all of these are going to have a positive 3 out front, and then we're just multiplying by these numbers that we wrote. And we're going to get 0, 3, 6, and 9. So what we're going to get is, and x is negative 3. Okay, the scaling is way off on this, so it looks like they go by sixes. So this would be minus 6. This would be minus 12. So minus 3 is about here. You're up at around 9. And then minus 2, you're up at 6. So you're right here. And then minus 1, you're at 3. So you're down here. So it's kind of hard to see with these little, it's really kind of zoomed out here. But then we notice when x is 1, I get 3 again. And then when x is 2, I get 6 again. And when x is 3, I get 9 again. So it's the same numbers, whether x is positive or negative. So this would be the function. D is the answer. And now we can kind of look at this and decide what is it doing. So D is the answer. And I don't have the blank shown. It basically says, are there any excluded values of y, and then what's the range? So an excluded value would be like a hole in the graph or a gap. So a hole or gap would be what they call excluded values in the range. But notice there's no holes or gaps in this. It's two smooth lines that are, now they do stop, so they stop at 0, but they're going to go off to infinity, to the left and to the right, and straight up. So the range would be, it starts at 0, and it includes it because it does touches it right here, and then it would go to infinity. So that's where you'd have to put for the second part of this problem. The graphing is the tricky part, but just pick some x's, calculate your y's, do a quick sketch, and you'll kind of see what the thing is doing. Okay, so for 11 and 12, we're going to skip those because you're not going to see them on the homework, and they're just a little bit beyond what we need to cover in this course. So 11 and 12, you're going to skip. Don't worry about those. And that will complete section 2.2.